Trying to get started with this new Max II. It's called a CPLD, Complex Programmable Logic Device. And you can write a lot of cool code on this thing. We're going to do some cool projects with it. But to get started, I just need to figure out first how to power this thing. It comes with this blaster. It's called a...
Here's the cover.
Yep. Okay, so USB blaster. This blaster, it does not power the device. I was looking at that, and this is the data sheet for the USB Altera blaster, and it says right there VCC target. I was like, oh, okay, it's supposed to power it, and then I looked and realized, no, target supplied by the device board. So that means basically the power in here supplied back to the blaster, and that's probably just to make sure that the board has power before programming. So I'm not going to power it that way, obviously. Now I got to go with the jack. Unfortunately, there's not a pin out for this or anything, so I wasn't even sure what was, is the pin positive or negative. I wasn't sure. So I started kind of looking through this whole circuit, trying to reverse engineer it, and what I came up with is this. So it looks like this chip here, right here, it's the AMS 1117, and that's supposed to provide 3.3 volts to the Altera Max II. And this chip basically turns the extra voltage coming in on here into heat. So if you have 5 volts coming in on here, it'll take this voltage, turn it the rest into heat, and then it regulates it down. So looking at it, I was able to come up with this circuit. So VCC can be 5 volts, and actually the chip supports up to 18 volts, but the more voltage you have, the more it turns it into just plain power dissipation. And then it regulates at 3.3, and there's a little switch in there. So I kind of did the reverse engineering on that just to make sure. And then I also want to find out how much can this voltage linear regulator actually produce, how much current can it output. Interestingly enough, I have an Arduino and a little Ethernet board, and they both use the same linear regulator.
That chip there.
Yeah, actually both of those right there are linear regulators. Whoops, sorry. Both of them are linear regulators. So, basically, long story short, I just want to see how much power these things could output at 5 volts in. So right here is a little data sheet. It tells you max junction temperature is 150 degrees C. And it turns out that it says right here power dissipation, which is really all we're worried about. It says milliwatts, but it says C note 1. So I was like, okay, what? I've got to calculate something. So it depends on what temperature you're actually at. So TJ max minus temperature ambient. So temperature of the junction minus the temperature of the ambient.
What's the junction temperature?
The junction temperature is the actual die temperature inside the chip, or the actual individual parts.
So it's not the outside of this chip here.
No.
It's the inside.
Yep, that would be the ambient temperature of the air.
Oh, yeah.
So basically this formula here, or these numbers, based on what package type, because these chips are sold with different packages. And our chip actually, this is wrong, it's not 102, it's 88 degrees per watt. So essentially it's telling you how well this chip can dissipate heat into the air. And so obviously the bigger the chip, the more surface area it has and how much it can dissipate. Well, it turns out we have 88, which is better than 102, because that means it can dissipate better, more heat.
So does that mean that this chip's like a really small chip?
Yeah, it's definitely smaller. And I think if you actually look at, so when I took apart the PB blaster, or not PB blaster, that's for wrenches, dude. Okay, so when I took apart this blaster, it looked like there was a linear regulator in here too. If I point it out, it looked like, I think this is a linear regulator. Let's see, right there.
So that might be one of those small
It might be one of
packages.
some, but the text on it was more like a date code, so I'm not sure what actually is that, but that's why I think that is a linear regulator. But this chip consumes a lot more power, and any other peripherals you might have on there. So I just want to get an idea. So what this formula comes out to be, 150 minus 35 divided by 88 gives you 1.3 watts. That's the total amount of power this thing can produce or dissipate at 35 degrees C, which is 95 degrees Fahrenheit. Well, that comes out to be 260 milliamps at 5 volts.
So this is the max power you could supply if you're in this temperature environment.
Yep. So actually, as I was talking about this, I realized that So and you'll probably see this too. So if here's your device, it's putting out 3.3 and it's taking in 5. So really you have a 1.7 voltage drop across that. Well, then that means your power of this device, which is the power we calculated over here, is really the 1.7 volts. And so it's 1.3 divided by 1.7. So actually, this shouldn't have been 5 here. This should have been 1.7. And then that should have come out to be 0.7 amps, 0.76 amps, or 760 milliamps. So this actually is not too bad. That's almost an amp of power we can put out, and there's no way this chip is going to use 1 amp of power. But anyway, so that's what, just quick to get started. And then the next thing, so now we know how much power this thing can put out. We also know what voltage this thing can handle. Finally, what we have to do is figure out how to power it. So I was looking for barrel jacks to plug into here, and this is what I came up with. Unfortunately, it was already tied into another power supply. So I end up with a lot of power supplies like this because I harvest the barrel jacks on them.
So this one was off of 12 volt.
Yes. Yep, that was off of 12 volt. Now, what to put on here, so I still need 5 volts because the 12 volt wasn't going to work. So I got
Why didn't we use the 12 volt one?
Well, we could have.
Could have.
You probably could have, but then your numbers all change, and then then if I want to use that 12 volts, 5 volts for anything else on the board or anything.
Because you might want to run off your computer.
Yeah. Well, no, I mean, yeah, I just don't want to. I don't want to having to do with 12 volts on this circuit if I can help it. I could power it on a USB cable, which I will do, but I'll put it with banana jacks here. And I'll put some banana plugs in here. So then if I want to power this board off of a power supply, or if I want to power it off of something else, I can just use the banana jacks. It turns out I have a handy kit here with little different types of banana jacks. So the good ones are actually underneath. Kind of hide them from everybody else. So you can stack them together. So now basically red is connected to black. You stick the wires in from this side, and then you can. There's a screw inside there to screw down the wires, and I'll show you how to do that. All right, so if you have the wire stripped and ready to go, all you got to do is take this, take it, you unscrew the little flathead screw in there, stick the wire in. Now it's tightened in. So all right, we're ready to plug this thing in. So we're gonna plug this in and see what happens. So switch is off, I believe. Yep, see, it works. Yep, that's good. I like that. And that's supposed to be blinking, and I have a power light. So we release now, we have it powered up, and then we're gonna talk about how to program this thing. We're gonna do some projects with it.